Hello, this will be a lecture on panel data models. In this lecture, I will talk about the following things. First, we will talk about panel data characteristics and the types of panel data that are available. Next, we will talk about variation types, particularly the overall, within, and between variation. Next, we will discuss panel data models, including the pooled model, fixed effects model, and random effects model. And then we would switch to talking about estimators and properties. First, we will talk about consistency and efficiency, and just providing definitions for those. And then we will talk about different estimators that we can use to estimate these panel data models. And they include the pooled OLS between fixed effects, first differences, and random effects estimators. And then finally, we will talk about the tests for choosing between the models, including the Fagin test and the Hausman test. Okay, so let's begin. First, let me give a couple examples of panel data models. For example, in labor economics, we could be studying the effect of education on income. So income would be the dependent variable, and education would be the independent variable. And the most important thing here is that we would have data across time and individuals, and that's what makes it the panel data model. Or another example is that we can study the effects of income on savings, and this time the data could be across years and countries. So we have two dimensions. One of them is the cross-sectional dimension, like countries, individuals, firms, or any kind of objects or subjects. And then we have the second dimension is time series dimension, which is either years, months, minutes, or something like that, or different periods. So what are the characteristics of panel data? The most important thing is that, as I talked about, it provides information on individual behavior, and that is both across individuals and over time. So we have this cross-sectional time series dimension. So our notation would be that the panel data includes n individuals observed at t regular time periods. So the dimension of our data would be n times t if we have complete data, all individuals that are observed for all years. So this is the case where panel data is called balanced, when all the individuals are observed for all time periods. Or the data could be unbalanced when some of the individuals are not observed for all time periods. And nowadays computer software is really good about dealing with unbalanced panel data. So when we talk about panel data models and estimations, we're going to assume correlation or clustering over time for a given individual, but we would assume independence over individuals. So what does that mean? In the example that I have here, we could have that the income for the same individual is correlated over time. Why? Because maybe the person has same job or same skills or something like that over time. But that is independent across individuals. So my income is independent of the income that you have. So here's several panel data types that could exist. First one is short panel, where we have many individuals and a few time periods. And this is the case that we will use in this class. You could also have long panel where you have many time periods and a few individuals, or you could have both where you have many time periods and many individuals. This is rare though to have such a rich data set. So let me talk a little bit about the regressors that we could have. The first one is a varying regressor. And as you can see here, we denote that by XIT. And you can see both the I index, which is for individual, and T index, which is for time. So that could be annual income for a person or annual consumption of a product. Why? Because it varies both by the individual and by time. Next, you could have time invariant regressors. So you could have xit equals xi for all t, which means you basically have the same value for an individual over time. And these could be gender, race, and education. So that's not to say that these can't change over time. Everything's possible nowadays. But it means that it so happened that in the data it didn't change. So we could possibly have the time invariance on these, meaning every person has different value, but that stays the same over time. And the third type of regressors that we could have is individual invariant regressors, which is xit equals xt for all i's. So in this case, basically, we have a variable that does not change across the individuals. So that could be something like a time trend, economy trend, such as unemployment rate, or anything that's valid that changes over time, but it doesn't change over the individuals. So again, 3 different types of regressors that we have. Okay, so here in this table, I wanted to illustrate the differences between overall variation, between variation, and within variation. So the overall is variation over the time and individuals. The between one is a variation between the individual, meaning from one person to the next. And the within variation means variation within individuals over time. So basically, how does my income change over time? But it's not compared to yours. In contrast, the between variation would have how does income varies from me to you to somebody else and so on, and not taking into consideration like our average income, but not how it changes over time. Okay, so here's one table that I came up with. I totally made up all the numbers, but I just wanted you to see how these numbers are calculated. So the first column that we have here is ID, and that would be denoted by I. And say we have the first ID has 3 observations, the second person has 3 observations, the third person has 3 observations. The next column here is time, and let's call this 1, 2, 3, 1, 2, 3, 1, 2, 3. So this is probably a bad notation because these numbers are the same, but you could call this as years, say 2011, 2012, 2013, or something like that. And so here we have an example of a balanced panel data where we have all the times are available for all the individuals. So then suppose we have a variable xit, and these are the values for each individual. And again, I totally made up these numbers, and I can't even give an example of what this could be. So it's a totally like made up number. So look at the first individual. He has values of 9, 10, and 11. The second one, higher numbers, 20, 20, 20, but it doesn't vary. And the third one is 25, 30, and 35, even higher means, but they also vary a lot, as you can see. So how do we summarize data like that? The first thing that we can look at is individual mean, or we would call this xi bar. So you see that from here, from xit to xi bar, one thing that disappears is t, the time dimension, and we're taking the average over time. So we're taking the average over time of the first person, xi. So the average of 9, 10, and 11 is 10. And that number is repeated, and it's now the same because it does not vary over time. The average of 20, 20, and 20 is 20. And the average of 25, 30, and 35 is 30, and that's repeated. So that's how we take individual mean. We're taking the mean and getting rid of the time dimension. Next one is the overall mean. So you basically are taking the mean of 10, 20, and 30, and that's 20. And so you see how it has xi, no I or t indices anymore. So we only have one number for the whole data. So the overall variation, again, that would be the variation over time and individuals. So the way to calculate this is xit here minus the overall mean x bar. So we have this number 9 here minus 20, and that would be a number minus 11. Or we would have 10 minus 20, and that would be minus 10, and so on. So this guy has a 0 because the overall mean is 20 and he has values of 20. And this one's would be 5, 10, and 15. So this is the overall deviation. So the next thing to calculate is the between variation. So this will be a variation from one person to the next. How do we do that? First of all, we look at the individual means where the time dimension is removed. And next, we subtract from that the overall mean. So we have the individual mean of 10 minus the overall mean of 20, and you have minus 10. Then you have the individual mean 20 minus the overall mean 20, that would be 0. And individual mean minus the overall mean, that would be 10. So notice again, the between variation is only how numbers differ from one individual to the next. But there is no time dimension in those because there are no time indices here. We have first averaged everything over time, and now we're thinking about differences between people. The next one is just the opposite, which is the within variation. So we want to know how do these numbers vary for one person only. So we would take the variable xit minus xi bar. So we have xit 9 minus xi would be 10, and we have a number of minus 1. So then we have 10 minus 10, that's 0, and that's 1. And so these values are 20 minus 20 is 0, and so on. You have 25 minus 30 is minus 5. So notice one thing that we have. So here the within variation, we have a very small within variation for the first person, which means that their values of 9, 10, and 11 don't vary too much over time. For the second person, their values of 20 don't vary at all over time. And for the third one, we have the highest within variation with minus 5, 0, and 5. They have very variable over time. But notice one more thing about the numbers here is that we don't know too much about the levels anymore, because this guy has an overall mean of 10, this one has an overall mean of 30, but you can't see that from the within variation. So one thing that sometimes the software do is they add back the overall mean to kind of get also at a certain level for these variables. So here to this number you're adding the overall mean of 20, to this number you're getting the overall mean of 20, so you're basically increasing the whole level by 20. And these are the numbers that we have here. And again, we see that there is the smallest variation, well, the smallest variation is here, which is 0, and then this one is basically the highest variation among them. Okay, so hopefully this table was useful to illustrate differences between overall, between, and within variation with a simple example. So let's go ahead and now look at the different formulas that we have. So for the individual mean, how do you calculate the mean? It's xi bar, and you do a summation over t, and you divide by capital T, the number of periods that you have. So you're removing the time dimension and you're calculating the average for each person over time. Now the overall mean takes the average both over the individual and over time of xit. Next, we have the overall variance. And so the overall variance is how each individual variable, xit, minus x bar, this is the overall mean, And then you have, this is a formula for the variance, both over individual and time. So for the between variance, the formula that we have is xi bar minus xi. So this is the overall mean, and that's the individual mean. So notice that for the between variance, you have no time dimension. It's already been taken out when you were taking the bars. Now, on the other hand, when you have the within variance, you have xit minus xi bar. So here we're not looking at comparison between individuals, only within. And you have each individual value minus its mean going into the formula for the variance. And now this is also equivalent to if you add the overall mean, or the last column that we talked about on the previous slide. Because it actually, this one, because it's a constant, it doesn't have any variance. So the overall variation can be decomposed into between and within variation, and generally the variation, the overall variation, is approximately the summation of the between and the within variation. So we already talked about that, but time invariant regressors such as race, gender, or education would have zero within variation. Why? Because they don't vary over time. So therefore their mean would be exactly the same as all the values, and when you take each individual value minus the mean for the individual, you will end up with zero. So individual invariant regressors, they would have zero between variation. Why? Because they may vary over time, but their variation is exactly the same for each individual because it doesn't vary. Okay, and so one thing that is common is when you do your own problem is to check if the between or the within variation is larger for each variable, because you want to get a sense of how your data varies over time and over individuals. Okay, so next we will talk about panel data models. And they're used to describe individual behavior across time and individuals. There are three types of models: the pooled model, the fixed effects model, and the random effects model that I'm going to talk about. So let's go ahead and start with the pooled model. So the pooled model would specify constant coefficients, which is the usual assumption for cross-sectional analysis. So if you look at this, you have a dependent variable yit, you have the independent variable of xit, and you have coefficients that don't vary. So this model just takes the data and applies RLS model to it, kind of like ignoring the fact that it's panel data. So that's the most restrictive panel data model, and it's not used much in the literature. The next ones, which are much more popular, are called individual specific effects models. So we would assume that there is unobserved heterogeneity across individuals captured by alpha I. So, for example, that could be an unobserved ability of an individual that affects wages. So we have something alpha I that's pertaining to that individual, but that's the same for the individual over time. So it doesn't change over time for a particular individual, but it's different from one individual to the next, and that's why it has only I as subscript. So the main question that we have here is whether these individual specific effects alpha I are correlated with the regressors. If they're correlated, then we have the fixed effects model, and if they're not, we would have the random effects model. So let's explore this in a little bit more detail. So the fixed effects model would allow those individual specific effects alpha I to be correlated with the regressors X. And we would include alpha I's as intercepts. So each individual would have different intercept but the same slope parameters. So notice here we would have yit, and then we would have here xit, But notice that this alpha, instead of just being alpha, it's alpha I. So we're now allowing that parameter to vary across the individuals. And after we estimate the model, we could recover those individual specific effects by doing alpha I hat, and that would be equal to yi bar minus xi bar beta. So we're removing the time effects from both the dependent and independent variables because this alpha I doesn't change over time, and we're using beta hat, the predicted values, the coefficients, the estimated coefficients here that we have, to get the predicted values for alpha I. So these individual specific effects would be the leftover variation in the dependent variable that cannot be explained by regressors. So therefore, if you have like a model of how education affects income, and then you can say, okay, there's so much that I can explain with the model and my beta coefficients, and the rest I can't explain it, except I know that that person for some reason gets higher income, and that person for another reason gets lower income than predicted. So in this case, we could also have time dummies that could be included in the as regressors because they could vary over time. The random effects model, on the other hand, assumes that those individual specific effects alpha I are distributed independently of the regressors. And in this case, we would include alpha I in the error term. So each individual would have the same slope and a composite error term that would come from the EIT, the normal one, and alpha I. So here, if we take the variance of the error term, we could have sigma alpha squared and sigma e squared, and the covariance of these two would be sigma alpha squared. Why? Because these are independently distributed, so they'll fall out. So that's why we only have the sigma alpha squared. So rho, or the correlation between two of these errors for between time period t and s, would be equal to sigma alpha squared divided by the summation of these two. So this rho would be called the interclass correlation of the term, and rho would be the fraction of the variance in error due to the individual specific effects. So if it approaches 1, the individual effect dominates the idiosyncratic error. This means this and this is so large that this doesn't make too much difference, and we would have a 1. Now, if we have too much of idiosyncratic error, and this is too high, but these two are kind of, but the sigma alpha square is kind of low, then we have rho, the correlation being 0. So in certain ways, we want this rho correlation to be high, because in this case, we can at least say we don't know what it's due to, but we know that there's something about that person that makes this variation high. Okay, so now we would talk about panel data estimators. So we talked about the different models, and now it's time to estimate them. And these estimators would differ based on how they consider the between or within variation in the data. And their properties, and particularly the consistency, would differ based on which model is appropriate. So let's digress a little bit and talk about estimator properties in general. So one thing that we prefer is estimators that are consistent and efficient. So we first check for consistency and then for efficiency. What does consistency mean? Consistency means the distribution of beta and hat would collapse to beta as n becomes large, or that would be the limit. So it is based on the law of large numbers, and it means that if you have more observations, they will tend to provide more precise and accurate estimates. So consistency means you have more estimates, you're going to basically get as close as possible to a very, very precise and accurate estimate. Okay, on the other hand, efficiency or minimum variance is established relative to a class of estimators. So some of you have probably heard that the OLS is efficient or minimum variance among the class of linear unbiased estimators, or the maximum likelihood estimator is asymptotically efficient among consistent estimators. So what we want here is, if the most important thing is consistency, we want an estimator that gives accurate estimate. Then we want an estimator that has as low as possible variance, and that is called efficiency. So these are the two things that we will look for, the estimators, and we'll come back to that topic in a few slides. So let's go ahead and consider different estimators. The first one is the pooled OLS estimator. That one uses both between and within variation, and it's obtained by stacking the data over I and T into one long regression with NT observations and estimating it by OLS. So what you have here is YIT, and then you have XIT here, alpha and beta, and everything else goes into the error term. So completely ignoring the fact that we're dealing with panel data. So if we have that the true model is a pooled model and the regressors are uncorrelated with the error term, we would have that the pooled OLS regressor is consistent. But if the true model is the fixed effects, then the pooled OLS regressor would be inconsistent. And we typically need to have panel corrected standard errors with this kind of model. But in general, I don't think that many people would use the pooled OLS estimator, because we have better estimators to estimate panel data models. So here's one of them. The between estimator only uses the between variation across individuals. So it would use the time averages of variables. So what are these time averages? So if individual has work experience, say, of 9, 10, and 11 years measured over 3 periods, then the average of this experience would be 10, right? The average of these 3 numbers. And so this would be an OLS estimation of the time average dependent variable on time average regressors. So instead of using YIT here, you use YI bar, that you have averaged the information over T. And same thing for X, you have averaged the information over T. So the number of observations is N, and the time variation is not considered because the data are collapsed with 1 observation per individual. So this estimator is not used very much because the pooled and RE estimators are more efficient. And also, if you have basically panel data, then why take away all the within variation and only consider the between variation? You're throwing a lot of data here by averaging things up first and then coming up with the estimates. So for the within estimator, also called the fixed effects estimator, they would use the variation over time or the within variation. And it would use the time d-mean variables. We would have individual specific deviation from their time average values. Okay, so what does that mean? If individual has work experience of 9, 10, and 11 years measured over 3 periods, the average experience would be 10. So the time d-mean values would be 9 minus 10, that would be minus 1, 10 minus 10, that would be 0, and 11 minus 10, that would be a 1. So instead of using the original variables here, we would use these time d-mean variables. So this would be an OLS estimation of the time d-mean, dependent variable and time d-mean regressors. So notice that instead of just having YIT on this side, we have YIT minus YI bar, which means this is the average for each individual, and we're taking this away from the original variable. So we're dealing here with time d-mean regressors. And same thing for XIT, we're taking away the average for that individual. So some software packages would estimate, instead of just like taking this number, they would put back the overall mean for these. And that's okay. So the number of observations here would still be NT, because we still have YIT, even though we're demeaning that. And notice another thing is that the individual specific effects alpha I cancels out. Why? Because if we are taking the average of alpha I over time, that would still be alpha I. So then we have alpha I minus alpha I bar, and that would be a 0. So here alpha would be the average of all the individual effects. One limitation of these within estimators is that time invariant variables would be dropped from the models and their coefficients cannot be identified. So think about it. If you have a variable that is a female or a male, that would have values of 1 or 0 for a female dummy variable. So the values minus the mean for each individual would be 0, right? Because if I'm female, then the values would be 1, 1, 1, 1 over time. The average of that would still be 1. And if you take any ones minus the 1, which is the mean, that would be a value of 0. And same for males. So you cannot estimate a model that has time invariant variables. So if you're interested in considering those effects, we would need to consider different models, like an OLS model or between estimators. Okay, another estimator that we will consider here is the first differences estimator. And this estimator uses one period changes for each individual, so from one period to the next. And it would use the first difference variables. So let's consider this example. If individual has work experience of 9, 10, and 11 years, then the first different experience would be missing, 1, and 1. Missing is because 9 minus, we don't know the value in the previous period, so that's why it would be missing. 10 minus 9 would be a 1, and 11 minus 10 would be a 1. And so that's how we are going to have these values. And notice that we will always be losing, like we would have as many numbers here as the number of periods minus 1, because we would be losing the value for the first one. So this is the OLS estimation for one period changes of the dependent variable and one period changes in the regressors. So notice that here we have a YIT, and here we have YIT minus 1. So we're taking the difference from one period to the next, same for the dependent and same for the independent variables. So the number of observations would be n, and t minus 1 because we're losing the value for the first observation. And also the individual specific effects alpha I cancel out. Why? Because they're the same over time, and if you take alpha I minus alpha I, that would be 0. And so a limitation of this model is that, again, time invariant variables are dropped from the models and their coefficients cannot be estimated. Okay, so the final estimator that we will consider is the random effects estimator. And this is an OLS estimation of the transformed model. So instead of just having alpha IT as a dependent variable, we would do minus lambda hat alpha I bar, and same thing here for xi. Okay, so one thing to notice here, and I have this point in the third bullet point, is that if this lambda I is 0, then we would have this term drop out, right? So that would be equivalent to the pooled OLS model. And if we have lambda hat, if that's equal to 1, that would correspond to the within estimator, because then we would have YIT minus YI bar, and that would be the same as the within estimator. And any case in all the other cases would be something in between. Okay, in this case, I included a little bit more information on the error term and on lambda, how you can estimate this lambda. Okay, the number of observations would again be n times t. The individual specific effects in this case would be in the error term. And notice that these random effects would be a weighted average of the between and the within estimates. And another property of this estimator is that it would be fully efficient under the random effects model, but not if the fixed effects model is correct. Okay, so let's now look at all the models that we have and all the estimators that we can use to estimate these models. So here are the three models, and we're assuming that these are true. The pooled model could be true, the random effects model could be true, or the fixed effects model could be true. And these are the estimators that we can use to estimate those three models: the pooled OLS, between, within, first differences, and random effects. So the fixed effects estimator, this one right here, you see that it gives you consistent estimates in all cases. And this is very, very desirable because we first want consistency. But they may not be the most efficient always. So the random effects estimator here would provide consistent estimates, but they would be inconsistent if the fixed effects model is the true model. And the random effects model is consistent and most efficient if the appropriate model is the random effects model here. So we would need to have a test, and that's where we're heading, to decide should we use the fixed effects model or not. Because if we have inconsistency, we would rather stick with the fixed effects model. But on the other case, if we have consistency, then we want to concentrate on the one that has the lowest, the best possible efficiency, and that would be the random effects estimator. Okay, so these are the tests that we're going to use to choose between the fixed and random effects models. The first one is the Fagin Lagrange multiplier test, and this is actually a test for random effects model based on the OLS residual. So what we are testing for here is whether sigma u squared, or equivalently the correlation of these error terms over time, is significantly different than 0. So if the Lagrange multiplier test is significant, we would use the random effects model instead of OLS. But we still need to test for fixed versus random effects. And actually, from my experience, most all the time, you would have a support to use one of the true panel data models, like either the fixed or the random effects model, rather than the OLS model. So the Hausman test is the real test that you need to use every time you have panel data. And the random effects model would be more efficient, so we need to use it if the Hausman test supports it. If it doesn't support it, then we use the fixed effects model. And so the Hausman effects tests whether there is a significant difference between the fixed and random effects. And the Hausman test statistic can only be calculated for time varying regressors. So what is the Hausman test statistic? Here we have betas coming from the random effects model and betas coming from the fixed effects model. And you have here again betas coming from the two models. We're taking the difference, and that's the variance covariance matrix. So if these are close to each other, that value would be close to 0. And if they're very different from each other, that value would be farther away from 0. So this test is distributed as chi-square, and the degrees of freedom are equal to the number of parameters for the time-varying regressors. And so if the Houseman test is insignificant, then we use the random effects. So it basically doesn't matter. Both of them would be consistent, so we might as well use the random effects. But if the Houseman test is significant, this means that if we use the random effects estimator on the fixed effects model, then we're going to get inconsistent results, and that's a bad thing. So we want to use the fixed effects model. Okay, so that was the lecture on panel data models. We talked about the different models, different estimators, and how to test the models. So next is considering an example of panel data with real data and several programs to estimate panel data with. Thank you for watching.